Welcome to DAR Tutors. Today, we will explore Chapter 28 of the IB Mathematics, Applications and Interpretation. Higher Level Curriculum, the Normal Distribution. This chapter is fundamental to statistics. We'll introduce the normal distribution, learn how to calculate probabilities using it, explore the concept of the standard normal distribution, and finally, learn how to find quantiles. Our learning objectives for this video are to introduce the concept of continuous random variables and the probability density function, define the normal distribution, and understand its key characteristics. We will also learn how to calculate probabilities using technology for both the general normal distribution and the standard normal distribution, find quantiles using the inverse normal function, and tackle several IB-style problems. First, let's understand the difference between discrete and continuous random variables. You might be familiar with discrete variables, like the number of heads in a series of coin flips, which can only take on specific separate values. In this chapter, we focus on continuous variables, which can take any real value within a given range. Think about a person's height, a fish's weight, or the time taken to complete a task. These can be measured to any degree of precision. This continuous nature has a critical consequence. Let's consider the weight of an egg. The probability that an egg weighs exactly 72.9 grams to an infinite number of decimal places is 0. No matter how accurate our scale is, a reading of 72.9 grams simply means the weight is within a range, say between 72.85 and 72.95 grams. This leads to a key rule for continuous variables. The probability of a variable taking a single specific value is always 0. Because of this, we can only talk about the probability of a value falling within an interval. A range of values is needed to have a non-zero probability. This also means that for continuous variables, inequalities do not change the probability. For example, the probability of x being less than or equal to d is the same as the probability of x being strictly less than d. So if we can't use a probability mass function to describe a continuous distribution, what do we use? We use a function called a probability density function, or PDF. A PDF, denoted f of x, is a curve. Unlike the bars of a histogram, the value of f of x at any given point is not a probability. Instead, probabilities are represented by the area under the curve over a specific interval. For example, the probability that a continuous variable x falls between two values, c and d, is equal to the area under the PDF curve between x equals c and x equals d. Two crucial properties of any probability density function are: first, the function must be non-negative everywhere, meaning f of x is always greater than or equal to 0. You can't have a negative probability. Second, the total area under the entire curve must equal 1. This represents 100% certainty that the variable's value will fall somewhere on the real number line. Now let's introduce the star of our show, the normal distribution. It's the most important distribution in statistics. Its probability density function produces a symmetrical bell-shaped curve. This pattern appears naturally in a vast number of real-world phenomena. Why is it so common? It arises whenever many different independent factors affect the value of a variable. Let's think about the weight of apples from an orchard. The weight of an apple is influenced by countless factors: genetics, soil quality, sunlight exposure, rainfall, temperature, and so on. Most apples will have a weight centered around the average, with fewer apples being extremely heavy or extremely light. This multitude of factors leads to a normal distribution. Some examples of quantities that are often normally distributed, or at least approximately so, include the heights of people, the lengths of adult sharks, crop yields, the volume of liquid in drink cans, and the lifetimes of batteries. In all these cases, we have a central value, the mean, around which most of the data points cluster, with decreasing frequency as you move further away from that mean. Although all normal distributions are bell-shaped, their exact location and shape can vary. This is determined by two parameters: the mean and the standard deviation. The first parameter is the mean, denoted by the Greek letter mu, which measures the center of the distribution. The second parameter is the standard deviation, denoted by sigma, which measures the spread of the distribution. If a random variable x is normally distributed with mean mu and standard deviation sigma, we write it as x is distributed normally with parameters mu and sigma squared. Note that the second parameter is the variance, which is the standard deviation squared. The notation x tilde n of mu, sigma squared, is read as x is distributed normally with mean mu and variance sigma squared. Let's investigate how these parameters affect the curve. The mean, mu, controls the horizontal location. A larger mu shifts the entire curve to the right. The standard deviation, sigma, controls the spread. A smaller sigma results in a taller and narrower curve, indicating the data is more concentrated around the mean. A larger sigma results in a flatter and wider curve, indicating the data is more spread out. Let's summarize the key properties we've discussed. First, the normal curve is perfectly symmetrical about the vertical line x equals mu, the mean. This means the mean, median, and mode are all the same value. Second, the probability density f of x is always positive for all real numbers x, even though the probability of any single value is 0. The curve never touches the x-axis, which acts as a horizontal asymptote, meaning the tails extend infinitely in both directions. The points where the curvature changes from convex to concave are located at x equals mu minus sigma and x equals mu plus sigma. We've established that probabilities for a continuous random variable are found by calculating the area under its probability density curve. For the normal distribution, a special rule helps us estimate these probabilities based on standard deviations from the mean. This rule, known as the empirical rule, states that for any normally distributed population with mean mu and standard deviation sigma, approximately 68% of the data lies within one standard deviation of the mean, that is, between mu minus sigma and mu plus sigma. Approximately 95% of the data lies within two standard deviations of the mean. And approximately 99.7% of the data lies within three standard deviations of the mean. This means almost all data for a normal distribution falls within three standard deviations of the mean. Let's break this down into smaller specific areas under the curve. Since the curve is symmetrical, half of 68%, or 34.13%, lies between the mean and one standard deviation above or below it. This gives us 4 segments. Half of the remaining 32%, 95 minus 68, is 16%, so the 13.59% lies between 1 and 2 standard deviations. Finally, the remaining 5% is split in half for the tails, giving 2.15% between 2 and 3 standard deviations, and 0.13% in each tail beyond 3 standard deviations. This detailed breakdown is incredibly useful for solving problems without a calculator. Let's apply the empirical rule to a worked example. A school's grade 12 students sat for a mathematics examination. Their marks were approximately normally distributed with a mean of 75 and a standard deviation of 8. We can write this using our notation. The marks, let's call them x, are distributed normally with a mean of 75 and a variance of 8 squared. This gives us a mean of 75 and a standard deviation of 8. Let's start by calculating the key values for our curve. The mean is 75. Adding and subtracting the standard deviation gives us mu plus minus sigma, which is 75 plus or minus 8 or set in 83. Adding and subtracting twice the standard deviation gives us mu plus minus 2 sigma, or 75 plus or minus 16, resulting in 59 and 91. And 3 standard deviations give us 75 plus or minus 24, which is 51 and 99. Now we can sketch the bell curve. Our curve is centered at 75, with these calculated values marked at the appropriate standard deviation intervals. Now we can use our percentages. First, let's find the proportion of students expected to score between 67 and 91. Notice that 67 is 1 standard deviation below the mean, and 91 is 2 standard deviations above the mean. Using our percentages, we can sum the areas. From 67 to 75 is 1 standard deviation below the mean to the mean, which is 34.13%. From 75 to 83 is 1 standard deviation above the mean, another 34.13%. And from 83 to 91 is between 1 and 2 standard deviations above the mean, which is 13.59%. Adding these three percentages together, we get a total of 81.85%. So, we expect approximately 81.85% of students to score between 67 and 91. Next, let's find the proportion of students who scored more than 83. 83 is exactly one standard deviation above the mean. Since the curve is symmetrical, the entire area to the right of the mean is 50%. The area between the mean and one standard deviation above it is 34.18%. Therefore, the area to the right of 83 is 50% minus 34.3%, which is 15.87%. So 15.87% of students scored more than 83. It's important to remember that the empirical rule only provides approximate percentages for exact standard deviation intervals. For all other probabilities, we must use a calculator. The process involves numerical approximation, as the mathematical integral for the normal PDF is not straightforward. Thankfully, our graphic calculators have built-in functions to do this for us. Let's look at another example. The variable x is normally distributed with a mean of 40 and a standard deviation of 10. We want to find the probability that x is between 37 and 48. First, as good practice, we can sketch the area we're looking for under the curve. Here we see the mean at 40, and we want the area between 37 and 48. This shading is crucial for visualizing the problem. On your calculator, you will find a function, often called normal CDF. You need to input the lower bound of the interval, the upper bound, the mean, and the standard deviation. For this problem, our lower bound is 37, our upper bound is 48, the mean is 40, and the standard deviation is 10. After pasting and executing the command, the calculator gives us a result of approximately 0.406. We can also calculate the probability of a value being greater or less than a certain point. For the probability that x is greater than 40, we set the lower bound to 45 and the upper bound to a very large number, like 10 to the power of 99 to represent infinity. The result is approximately 0.309. Similarly, for the probability that x is less than 26, we set the lower bound to a very small negative number, like 10 to the power of 99, to represent negative infinity, and the upper bound to 26. The result is approximately 0.1081. This method allows us to calculate any probability for any normal distribution. We've seen that normal distributions are defined by two parameters, mean mu and standard deviation sigma. This can make comparing different datasets tricky. This is where the concept of the standard normal distribution comes in. The standard normal distribution is a special case. It is a normal distribution with a mean of 0 and a standard deviation of 1. It is denoted by z. Any value, let's call it x, from a general normal distribution can be transformed into a z-score. A z-score tells us how many standard deviations away from the mean a value lies. The z-transformation formula is z equals x minus mu, all divided by sigma. X is the value from our distribution, mu is the mean, and sigma is the standard deviation. A positive z-score indicates the value is above the mean, and a negative z-score indicates it's below the mean. A remarkable property is that if you transform an entire normal distribution of x values into z-scores, the resulting distribution of z-scores will always be the standard normal distribution, with a mean of 0 and a standard deviation of 1, regardless of the original mean and standard deviation of x. The z-score distribution has a mean of 0 because the mean of x mu becomes mu minus mu, which is 0. The standard deviation of the z-scores is the standard deviation of x sigma divided by sigma, which is 1. This transformation standardizes our data, allowing for direct comparison across different distributions. A primary application of z-scores is to compare values from different normal distributions. Let's look at an example. Kelly scored 73 in history and 66% in mathematics. At first glance, 73% looks better. However, the class statistics were different. In history, the class mean was 68%, and the standard deviation was 10.2%. In maths, the mean was 62%, and the standard deviation is 6.8%. We need to determine in which subject Kelly performed better relative to her classmates. To compare them fairly, we must standardize them using z-scores. A higher z-score means a better performance relative to the class. First, let's calculate Kelly's z-score for history. The formula is x minus mu over sigma. So we have 73 minus 68 divided by 10 and 2, which gives us approximately 0.49. Next, for mathematics, Kelly's score is 66, the mean is 62, and the standard deviation is 6.8. The calculation is 66 minus 62 divided by 6.8, which gives us approximately 0.588. Comparing the two z-scores, 0.588 for maths is greater than 0.490 for history. This tells us that even though Kelly's raw percentage was lower, her performance in mathematics was better compared with the rest of her class. She was almost 0.6 standard deviations above the mean in maths, but less than 0.5 standard deviations above the mean in history. We can now use z-scores to calculate probabilities using the standard normal distribution. A fundamental property is that calculating the probability for a range in a general normal distribution, p of x1 less than or equal to x less than or equal to x2, is equivalent to finding the probability for the corresponding range of z-scores, p of z1 less than or equal to z less than or equal to z2. While this was essential before calculators, it's now mostly a conceptual link. Our calculators can find these probabilities directly from the z-distribution. Let's find the probability that a standard normal variable z lies between 0.41 and 0.67. On our calculator's normal CDF function, we set the lower bound to 0.41, the upper bound to 0.67, the mean to 0, and the standard deviation to 1. The result is approximately 0.408. Visualizing this as the area under the standard normal curve between these 2 points helps build intuition. Similarly, for the probability that z is less than or equal to 1.5, we use negative infinity as the lower bound, 1.5 as the upper bound, and the standard parameters for the z distribution. This gives us approximately 0.933. The shaded area represents the entire tail of the distribution to the left of 1.5. So we can now use our calculator's normal CDF function to find the probability for any interval in a standard normal distribution by simply setting the mean and standard deviation to 0 and 1. We've learned to find a probability given a range of values. Now we'll learn the inverse, how to find the value or measurement given a probability. This value is called a quantile. Let's consider a population of crabs with shell lengths normally distributed with a mean of 70 millimeters and a standard deviation of 10 millimeters. A biologist wants to know what shell length corresponds to the 95th percentile, meaning 95% of crabs have shells shorter than this length. This is a quantile problem. We are looking for a specific value on the x-axis, k, such that the area under the normal curve to its left is exactly 0.95. Since 0.95 is greater than 0.5, we know k must be to the right of the mean 70. This is an inverse problem, so we use the inverse normal function on our calculator, often called inv-norm. The inv-norm function requires 3 inputs: the area to the left of the quantile we're looking for, the mean of the distribution, and the standard deviation. In our case, the area is 0.95, the mean is 70, and the standard deviation is 10. The calculator gives us k is approximately 86.45. This means that 95% of crabs in this population have a shell length of 86.45 millimeters or less. This is the 95th percentile. A very important note: many calculators, like the TI-84 Plus, always require the area to the left of the quantile you want to find. If a problem asks for an area to the right, you must subtract that probability from 1 to find the corresponding area to the left. For example, to find k such that the probability of x being greater than k is 0.2, you would first find the area to the left, which is 1 minus 0.2, or 0.8. Then you would input 0.8 into the inv-norm function. Always be mindful of this calculator-specific requirement. So far, we've only dealt with one distribution at a time. The IB exam often combines concepts from different areas, like probability and normal distributions. These are often called combined distribution problems. Here's an example. The times taken by students to complete a puzzle are normally distributed with a mean of 28.3 minutes and a standard deviation of 3.6 minutes. We are selecting 10 students at random. The first part of the question asks for the probability that a randomly selected student took at least 30 minutes to complete the puzzle. This is a normal distribution probability question. We need to find p of x greater than or equal to 30. Using our calculator's normal CDF function, with a lower bound of 30, an upper bound of infinity, a mean of 28.3, and a standard deviation of 3.6, we get a probability of approximately 0.3184. Let's store this value, as we'll need it again. Now for the second part. Out of 10 randomly selected students, what is the probability that 5 or fewer of them took at least 30 minutes? This part involves probability, but not the normal distribution. It involves a fixed number of independent trials, each with the same probability of success. This is a binomial distribution. Let's define a new variable, y, as the number of students out of 10 who took at least 30 minutes. The number of trials, n, is 10. The probability of success, p, for each trial is the probability we just calculated, 3184. The question asks for the probability that 5 or fewer students took at least 30 minutes, which is p of y less than or equal to 5. We use our calculator's binomial cumulative distribution function, or binom CDF, with n an ian shattered tens, p 0.3184, and x so 5. The result is approximately 0.938. So it's highly likely that 5 or fewer students out of 10 will take at least 30 minutes for the puzzle. As a 10-minute mark reminder, if you're finding this video helpful and are looking for expert personalized tuition in IB A-Level or IGCSE curricula, please don't hesitate to contact our tutors. We offer online and home tuition tailored to your needs. Now let's solidify your understanding with some IB-style practice questions. Question 1. The lengths of nails produced by a machine are normally distributed with a mean of 50.2 millimeters and a standard deviation of 1.1 millimeters. Nails are rejected if their length is less than 48 millimeters or greater than 52 millimeters. Find the probability of selecting a rejected nail at random. Pause the video here and try to solve it yourself. Sketching the curve can be very helpful. Let's work through the solution. The problem gives us the mean and standard deviation. We can write this as x is distributed normally with mean 50.2 and standard deviation 1.1. The probability of a rejected nail is the sum of the probabilities of being too short or too long. That is, p of x less than 48 plus p of x greater than 52. First, let's find p of x less than 48. We use normal CDF with a lower bound of negative infinity, an upper bound of 48, a mean of 50.2, and a standard deviation of 1.1. This gives us approximately 0.0275. Next, let's find p of x greater than 52. We use normal CDF with a lower bound of 52, an upper bound of infinity, the same mean and standard deviation. This gives us approximately 0.04351. Finally, we add these probabilities together. The probability of selecting a rejected nail is approximately 0.0275 plus 0.04351, which equals 0.0626. To three significant figures, this is 0.0663. So there is about a 6.63% chance that a randomly selected nail will be rejected. Here is question 2. The daily energy intake of Canadian adults is normally distributed with a mean of 8,700 kilojoules and a standard deviation of 1,000 kilojoules. Find the proportion of Canadian adults whose daily energy intake is between 9,000 and 1,000 kilojoules. Again, pause the video and attempt this on your own. Let's review the solution. We are given the mean and standard deviation. The problem asks for the proportion of adults whose energy intake falls within a specific interval. This is a direct application of finding a probability using the normal CDF function. The probability we need to find is p of x between 9,000 and 1,000. We will input these as our lower and upper bounds into the calculator. Using normal CDF with a lower bound of 9,000, an upper bound of 1,000, a mean of 8,700, and a standard deviation of 1,000, we get approximately 0.209. So, about 20.9% of Canadian adults have a daily energy intake between 9,000 and 1,000 kilojoules. Question 3 involves finding a quantile. The weights of the 545 babies born at a maternity hospital last year were normally distributed with a mean of 3.0 kilograms and a standard deviation of 200 grams. Estimate the number of babies that weighed less than 3.2 kilograms. Pause and consider this problem carefully. Notice the units are mixed. Before we begin, we must ensure all our units are consistent. The mean is in kilograms, but the standard deviation is in grams. We can convert the mean to 3,000 grams. This gives us X is distributed normally with mean 3,000 and standard deviation 200. We want to find the proportion of babies weighing less than 3,200 grams, and then multiply by the total number of babies, 545. To find this probability, we use normal CDF with a lower bound of negative infinity, an upper bound of 3,200, a mean of 3,000, and a standard deviation of 200. The result is approximately 0.8413. This means that 84.13% of babies are expected to weigh less than 3.2 kilos. To find the estimated number of babies, we multiply this proportion by the total number of babies, 545. 413 times 545 is approximately 458.7. Rounding to the nearest whole number, we estimate that 459 babies weighed less than 3.2 kilograms. Question 4. An industrial machine fills an average of 20,000 bottles each day, with a standard deviation of 2,000 bottles. Assuming production is normally distributed, on how many working days in a year of 260 working days would you expect under 18,000 bottles to be filled? Pause here. This problem is similar to the last one, with a slightly different wording. Let's solve this. First, we find the probability of a single day being an underproduction day, where X is less than 18,000. Using normal CDF with an upper bound of 18,000, a mean of 20,000, and a standard deviation of 2,000, we find this probability to be approximately 0.15587. This means there's about a 15.9% chance of producing less than 18,000 bottles on any given day. Now, we need to estimate the number of such days in a year. There are 260 working days. We multiply our probability by the total number of days, where 1587 times 260 is approximately 4126. So we would expect that on about 41 days of the year, fewer than 18,000 bottles would be filled. Our final practice question is another quantile problem. The marks for a mathematics examination are normally distributed with a mean of 57 and a standard deviation of 10. 10% of students received an A grade. What is the minimum mark to the nearest whole number required for an A? This question asks for a minimum mark that corresponds to a certain percentage of the distribution. It's an inverse normal problem. We are looking for a mark, let's call it K, such that the probability of scoring above K is 0.1 or 10%. This means P of X greater than K equals 0.10. Remember that our calculator's NV-norm function typically takes the area to the left. To find the area to the left of K, we subtract 0.1 from 1, which gives us 0.90. So we want to find the value K such that 90% of students scored less than K. This is the 90th percentile. Using NV-norm with an area of 0.90, a mean of 57, and a standard deviation of 10, we find K to be approximately 69.81. The question asks for the minimum mark to the nearest whole number. Rounding 6981 up, the minimum mark required for an A is 70. Any student scoring 70 or above would receive an A grade. Let's quickly recap what we've covered today. We started by defining continuous random variables and the probability density function, or PDF, where probability is represented by area. We then introduced the normal distribution, a symmetrical bell-shaped curve characterized by its mean, mu, and standard deviation, sigma. The empirical rule gave us approximate probabilities for data within 1, 2, or 3 standard deviations. We learned to calculate any normal probability using our calculator's normal CDF function. We also introduced the standard normal distribution, Z, with a mean of 0 and a standard deviation of 1, and the Z transformation to compare different datasets. Finally, we explored how to find quantiles using the inverse normal function on our calculator, which is the inverse of finding probabilities. Mastering the normal distribution is essential for your IB mathematics journey. Keep practicing with different types of problems, and remember to visualize the areas under the curve. For personalized support and expert guidance, visit dartutors.com or email us at info@dartutors.com. Thank you for watching. Remember, for more help and expert tuition in IB, A-Level, and IGCSE subjects, contact Dart Tutors.